Hello, I'm Charles Obour, professor at the University of Pau. Today I'm going to speak about serpentinization and hydrogen generation in Pyrenean Lherzolite. I did this job with Kenny Loiseau, a former PhD, and Isabelle Moretti. First, what about serpentinization? On the left, you have lazulite with olivine as a main mineral, and you put water in the system, temperature, let's say 100 to 300 degrees Celsius, and you obtain serpentine, peroxide, magnetite, and also H2, and you make a generation of hydrogen using this very well-known serpentinization reaction. I would like to point the Fa2 plus iron, and at the beginning you have only Fa2 plus. Then at the end of the product you have Fa2 plus and Fa3 plus, and meaning that you still have Fa2 plus in a serpentine, and so you can still obtain H2 afterwards. But I'm not going to speak about this late reaction. Most important point here is that you have a high reduction in density. You move from 3.5 to 2.4, and at the beginning, lazulite is paramagnetic, and after serpentinization, it's ferromagnetic with the large input of magnetite. That means that you can survey the serpentinization process using geophysics data like the Bouguer anomaly and the aeromagnetic anomaly. Let's go and see those data in the Pyrenean system. This is the Pyrenean system, sorry. The Pyrenean is from Cantabrian Mountains to so-called Pyrenees, which split Spain and France, makes the boundary. And we have here, I put not a precise location of H2 SIPs that we measure. And you have H2 SIPs in the north part of the Pyrenees and a small occurrence in the south part of the Pyrenees. I'm not going to speak more about this occurrence in the south part of the Pyrenees. And now let's have a look to the geophysical data. You have the Bouguer anomaly on the top, the magnetic anomaly lower, and the Bouguer is a proxy that you can use this proxy to see the pristine lazulite with a density of 3.5, let's say. And you have the magnetic anomaly, which is a view of serpentinized mantle body. And if you see at the Bouguer anomaly, there is a strip running from Bilbao to Tarbes, and where you indicates that the mantle is high, low depth, and the magnetic anomaly, you have a strip of non-homogeneous, this is patches of magnetic anomalies, which indicates that the serpentinization is very heterogeneous along strike of the Pyrenees. Of course, we can use those data to model the Pyrenees, the cross-section, and to match the data. This was done by Nicolas Lefebvre in 2022. And there is a good match, but look at the European mantle wedge. It is about 10-kilometer depth here. You have a very nice mantle wedge, and which fits with the geophysical data. Seismic data, magnetic anomaly data, and gravity data. At smaller scale, we have also this cross-section proposed recently by Nicolas Aspituri. And you can see the Bouguer anomaly, which is not in agreement with the magnetic anomaly. There is a shift between those two anomalies. One is clearly related to high density. This one is clearly related to content of magnetite, let's say. And the cross-section AB shows the mantle wedge again, but with a gradient of serpentinization, meaning that you have at least 10 kilometers of serpentinized mantle. So the moho is about 10-kilometer depth in this layer here, the purple layer from the Cantabrian Basin, Moline Basin, and Tar Basin. And this is within the serpentinization window, which means that today you can have serpentinization processes at this depth of the mantle. Why do we have the mantle at such a depth? I'm not going to extend this view, but you had 100 million years ago a rifting and hyperextension, and you bring the mantle up to the surface. Nicolas Lefebvre proposed a model recently, and so this is this cross section. You see the high topography, almost 2,000 to 3,000 meters high. You can have input of meteoric water, and this water is going at depth after a certain time, of course, and you have serpentinization here and release of hydrogen. This model is well accepted, but it's still a model, of course. The take-home message is that we had a mantle exhumation during early Cretaceous, and we had also high temperature serpentinization over a thickness of 10 kilometers. The geophysical data reveal a heterogeneous pattern of serpentinization along the Pyrenees, and hydrogen seeps have been detected above the mantle bodies, suggesting ongoing serpentinization. Let's have a look to the mantle body. And we have the chance in the Pyrenees to have almost 40 outcrops, very nice outcrops of mantle body. And for example, here, the Lherzolites, you have almost no serpentinization, while in the Saraye, you have fully serpentinized. So we have the whole range of serpentinization thanks to these 40 outcrops in the Pyrenees. That's the Lherzolite from Lherz. This is very weakly serpentinized, and those mantle rocks outcrops very near the surface. We know that because, for example, we have breccias associated with this mantle body. We have also a view of the Saraye Lherzolite and in the Sarans anticline. This example is fully serpentinized. If we use two proxies like the density, the horizontal axis, or the magnetic susceptibility, which is a nice proxy to evaluate the content of magnetite. If we look at the density from the two bodies, the Lherz mantle body and the Saraye mantle body, we are covering, you see, the whole range of density from 3.4 to 2.5 gram per cubic centimeter. This shows that there is a high heterogeneity in density within a single mantle body, and the density is used as a very regularly as a proxy of serpentinization. The magnetic susceptibility, you have here also a wide range of magnetic susceptibility, and in Lherz you have almost no magnetite, very few magnetite, while in Saraye you have quite a lot of magnetite. I will show you this using the microtomography, X-ray tomography. Magnetite is in yellow and the porosity is in red. So you see the Lherz, you have very small little dots of magnetite, while in the Saraye, where it's fully serpentinized, S is the serpentinization rate, and you see many magnetite in the Saraye. Let's have a closer look to the Turon mantle body. This is a very nice pyramid, as you can see, without vegetation except on the top. This is quite common in the mantle body to have a lack of vegetation on it. And we have a very nice access to mantle rocks here. We did magnetic survey, and you see here a positive magnetic anomaly above the mantle body. And why do we have this positive magnetic anomaly? It's because the paleomagnetic record of the mantle rock here is normal polarity. And this is really consistent with a serpentinization stage during the rifting process, because the magnetic field at this time was normal polarity during almost 40 million years. We also did a magnetic susceptibility survey, and here you see a very heterogeneous pattern of magnetic susceptibility at this scale of observation. And if we look at the closer scale, like metric scale, again, we have quite a heterogeneous pattern of magnetite content, which means that we have heterogeneity in serpentinization processes. And at small scale, you see that the distribution of magnetite is not homogeneous. And we have magnetite along shearing planes. And well, I didn't say that, but the Turon Lherzolite is a milonite, more or less. And you have protomilonite and ultramilonite on the right side. Take-home message is the following. First, the density measurements on the mantle body reveal a pronounced variability. For example, in Lerz, we move from 3.4 to almost 2.6. At the kilometer scale, we observe in the Turon mantle body a pronounced heterogeneity in serpentinization. And it's also observed at metric and micrometric scales. Okay, I'm a former paleomagnetist guy. I was doing PMAG, and I was study the magnetite in different settings. And now I would like to give you some more information about magnetite. Here you have this SCN picture, and the magnetite appears in white. Let's have a closer look. You have magnetite here, and also on the right side, spinel. And you see magnetite all around the spinel, which indicates that spinel act as a catalyst of magnetite formation. But also the magnetite itself, these appears as clusters, clusters of magnetite. And so what about those clusters? And we did some magnetic analysis. This is a fork diagram. I'm not going to explain this fork diagram, but there is a small cloud here. And this small cloud means that magnetites are nanometric in size and non-interacting. So that means they are not close together or stitched together. There is some distance between those nanometric grains. If we zoom in the SCN picture, probably this, which appears as a micrometric magnetite, is actually a cluster of nanometric grains. And that was quite surprising. So to figure out this organization, let's think about a galaxy. And the magnetite grains are the stars. So the clusters are some galaxies with magnetites distant each other with no interaction. This is quite a surprising view we repeat those measurements, and the literature shows also the same behavior. What we did also, it's a lab experiment, and during this heating lab experiment, we tried to make new magnetite, and we succeed in this project. And what was surprising is we are making magnetite, okay, in 24 hours, let's say. And the more we have magnetite at the beginning and the more we form magnetite during the experiment. So this clearly shows that magnetites act as a catalyst. And the more magnetite you have and the more magnetite you form, even at 100 degrees Celsius in lab experiment. That was a very nice study and it's almost published. It's at the end of the revision stage here. Okay, the take-home message number 3 is the following. During serpentinization, magnetite aggregates into clusters of hundreds of micrometers and characterized by remarkably consistent morphology. I didn't speak about this because I don't have time, but the clusters, they show exactly the same grain size distribution and shape also. This is quite remarkable. And those clusters consist of aggregates of nanometer-sized magnetite crystals with dimensions ranging from 20 to 100 nanometers in size. And the magnetite serves as a catalyst in redox processes. And this is quite important information here. Let's try to figure out the meaning of this. As a conclusion, there is a recent paper by Core, and in New Caledonia, they investigated peridotite, and they found nano. Well, they didn't say about nanomagnetite. They said about small magnetite that took place during high temperature serpentinization. The range of this temperature is 200 to 350. And we have clusters of nanomagnetite. It's what I show you. But you have also low temperature serpentinization, let's say at 100 degrees Celsius. And in this case, the magnetite is micrometers and even more than micron, tens of micron, hundreds of micron. This is big magnetite. And that means that when you have nanomagnetite, it's rather high temperature process, while when you have evidence for large crystals of magnetite, that means you have also low temperature generation of hydrogen, of course, during serpentinization. Well, I try to sketch here a very simple view of what's going on. If we start with pristine lherzolite, we don't have magnetite, or very few, and it's still debated, but we have very few magnetite in pristine mantle rocks. And when you get through the serpentinization window, you have heterogeneous pattern of serpentinization. We show this, I show you this on the maps at different scales. And also we have growth of nanomagnetite, but why don't we have larger crystals? It's because we have limited water input actually. And we have brief episodes of water influx. And when you continue this process, so you have magnetite, which is act as a catalytic, and so we group new nanomagnetite together. This is a model. We need to prove this model, of course, but I think this is quite what happened during serpentinization process. So that means that observation of nanomagnetites point to a discontinuous influx of water during high temperature serpentinization. To conclude, let's go back to hydrogen seeps. And we have here a map. The red dots is discrete hydrogen measurements that we did within the soil at 1 meter depth. And this is all those values are above the regional background. That is active drainage, I would say here. But if we are doing a continuous measurement here, it's a monitoring for 2 months. And what we see, it's a plateau. You know, we don't have, that's the blue symbols. We don't have any hydrogen for a certain time, then a sudden burst, then another burst, then again plateau, a small burst, burst, plateau, etc. So this is a very intermittent events, and that may reflect this continuous process at depth. I don't know if it had something related to serpentinization process that took place during brief episodes of water influx, influx, but probably there are several filters, of course, in the course of H2 propagation to the surface in the water, etc., blah, blah. But probably this continuous record that we have here could be related to this continuous process of serpentinization at depth. And this is my conclusion. So thank you very much.